So good morning, everyone. My name is Timur, and today I will be talking about some non-invasive diagnostics with pulse wave analysis. This is a rather interesting topic, and it connects well with our first today's speech. It has something common in terms of digital healthcare. So why is this important? This is important because pulse wave analysis lets us make some diagnostics, and very simple and non-invasive diagnostics on some serious cardiovascular diseases. So today I will be talking about results of two scientific groups. The first group is a hemodynamics modeling research group from King's College London. So the head of this group is Dr. Jordi Alastruey. If you're interested in pulse wave analysis or hemodynamic simulations, I highly recommend their website. This is probably one of the world's leading groups in this particular field. And I'm very glad that we have an opportunity to collaborate with them. And the second group is the group where I work. This is the Laboratory of Mathematical Modeling in Medicine in Sеченовский University. So Sечеnovский University is the first Moscow medical university. Recently, it started a lot of laboratories and research that involve mathematics and mathematical models. And this research is certainly part of it. Why study pulse wave propagation and pulse wave velocity, and what is the pulse wave propagation? So when our blood flows, it does not flow uniformly. It flows in pulses that start from the heart and go to the periphery. And this pulse wave has a lot of characteristics. And they're important for diagnostics. Also, they're important as parameters for various blood flow models. So this technique of pulse wave propagation analysis is very ancient. You can find some techniques from traditional Chinese medicine, few thousand years old. These techniques involve some study of the pulse and determining various diseases. So I'm not sure if these techniques are precise enough, but definitely there is something important about them. So now we're using this experience with more modern technologies. So on the left, you can see an example of pressure pulse waves that propagates through the time and through the coordinate along the aorta. And if you will track this pulse wave along the coordinate from the origin of the aorta to the farthest part, we can see that it deforms significantly. And we can kind of spot the speed of this wave, pulse wave velocity, if we will look at the foot of the pulse wave where it starts. And if we look at the pressure pulse wave under normal condition, it looks something like that. But if you have some kind of a cardiovascular pathology, if you've got some valvular stenosis or stenosis in aorta, then the pulse wave will change its shape. And if we can analyze the shape of this pulse wave, then thankfully, hopefully, we can predict some diseases with a simple methodics without the need of complicated invasive surgeries or complicated MRI or CT studies. So this is the idea behind pulse wave propagation analysis. And if we are able just to calculate pulse wave velocity, so the velocity of propagation of these pulses, this would be a very huge success, because the pulse wave velocity is a very important diagnostic parameter by itself. So here you can see a graph that shows survivability, or just the rate of cardiovascular events-free outcomes for patients with hemodialysis. And these patients are split into three groups, with low pulse wave velocity, middle pulse wave velocity, and high aortic pulse wave velocity. And we can see that group with high pulse wave velocity has very high rate of some cardiovascular events after 40 months. So knowledge of this pulse wave velocity gives us a lot of information about our patient. Can we leave this patient at home, or should we put him into intensive care? And typically accurately measuring pulse wave velocity is not that easy. So there are many techniques to measure pulse wave velocity. There are some empirical formulas that involve blood pressure and age. And more common methods are so-called foot-to-foot methods. This is the method when we measure pressure pulse wave, not necessarily pressure, maybe velocity pulse wave, into two points. For example, in carotid artery and femoral artery, or maybe in brachial artery and near ankle. And we obtain two pulses, and we can track, synchronize them with ECG, and get this delta t, the difference in time when pulses start. And then if we know the distance between these 2 points, we can calculate pulse wave velocity. So there are many options, there are many variants of this method. And because of that, if you want to test each new algorithm to calculate pulse wave velocity or to diagnose some kind of a cardiovascular disease, we need to carry out an extensive experiment. We need to find a large cohort of patients. We need to perform clinical studies. This is hard, expensive, it takes a long time. So a good alternative is a simulated pulse wave database. One of them was developed in King's College London, and here is the website for this database. So what is the simulated pulse wave database? So we take one-dimensional blood flow model. Each vessel is considered to be an elastic tube like that, and we want to calculate blood flow and pressure in each point along these arteries. So for that, we use some governing equations like mass balance, momentum balance, some other equations that involve elasticity of the vessel. I won't stop here. So we just construct a network of arteries from these elastic tubes. We calculate the redistribution of blood flow in junction points where few arteries meet. And then we impose some boundary conditions on the inlet. So this is cardiac output, systolic phase when heart pumps out the blood, and diastolic phase when our leaflets of the valves are closed. So we impose some boundary conditions, and we can solve these hydrodynamic equations in this one-dimensional graph of arteries. And we can calculate our pulse waves in various points. In various points of arteries, we can calculate blood pressure, blood velocity, blood flow area. So we have some kind of a baseline model of average patient. After that, we want to link this baseline model to an actual patient. For that, we can study which parameters of the model change with age and which parameters of the model do not change. So let's say we have 6 parameters, 6 key model parameters that change with age. For example, heart rate, stroke volume, which is the amount of blood that our heart pumps. So we can create some kind of a statistical study, and we can prescribe the average value of parameter to a certain age group. And then we can calculate plus and minus standard deviation. So for each age group, we have some average model, and we have 6 age groups. And for each age group, we change parameter. We take average value of parameter, then plus standard deviation and minus standard deviation. So we get 6 parameters and 3 values for everyone. So we got approximately 729 models for each age group, and we have 6 age groups, so we have over 4,000 virtual models. So we calculate some kind of a virtual population, and each subject of this virtual population has its own pulse wave, pressure pulse wave, blood flow pulse wave, And actually, this particular simulated database reflects reality rather well. So on the left, we have in vivo measurements. On the right, we have simulated measurements. And for various age group, we can see that our database can represent actual measured pulse wave velocity rather well. So we created this simulated database. Then what do we do next? Now we can use this simulated database for machine learning. So I won't stop on machine learning and neural networks here. I hope that everyone has a grasp on how it works. I will just say that for this first test, we created a simple neural network, and as input parameters, we used age, heart rate, stroke volumes, and systolic, diastolic, and mean brachial pressures. And as output parameter, we set pulse wave velocity. So very small amount of input parameters, just 6. And we wanted to know how accurately can we predict pulse wave velocity with these parameters. And to test, to validate our synthetic database and our neural network, we used actual measurements from 125 measurement patients. So these measurements were performed in Sечеnovский University. Each patient had cuffs on his brachial arteries and on his ankle. And we had readings of pressure values from these cuffs. So we had pulse waves in right brachial artery, left brachial artery, right ankle, and left ankle. And as you can see, there is some shift between the foots of these pulse waves. And thanks to these shifts, we can calculate the speed of pulse propagation because we know the distance between the cuffs. So we can measure these pulse wave velocities directly. So the idea behind this study is to measure these pulse wave velocities from the patients with foot-to-foot method between brachial and ankle pulse waves. And then we use generated synthetic database for training and try to predict pulse wave velocity of our patients. And then we compare them with actually measured pulse wave velocities. So the results can be seen here. Blue dots are cross-validation on synthetic data, and orange triangles are actual results for real patients. So we managed to predict pulse wave velocity with accuracy about 15%. And I have to say that 15% may sound like bad accuracy, but actually it's not that bad because pulse wave velocity ranges from 6 meters per second to 16 meters per second normally. And if we can predict it with the accuracy of 15%, it means we can distinguish at least high pulse wave velocity from low pulse wave velocity. And also we used very restricted amount of parameters that can be easily obtained from the patient. If we increase the amount of parameters, we can improve our accuracy. So thus we can use some kind of artificial intelligence method to predict pulse wave velocity, which is important diagnostic parameters from just easily obtainable measurements from the patient. So now this approach can be extended. This is an example of work from King's College London and Shanghai Jiatong University. In this work, they tried to detect aneurysm from pulse wave analysis. So aortic aneurysm is inflammation like this of aorta. This can be very dangerous, especially on later stages. And the problem is that on the early stages, it's very hard to detect it. And in this particular work, the goal was to detect abdominal aneurysm with photoplethysmography. So photoplethysmography is another kind of a pulse wave. Is when you have got like these light sensors through light shines through your finger, and you've got a signal like this one. And this signal turned out to reflect the pressure pulse wave very well. And this signal can be easily simulated with hemodynamic blood flow model that was described before that. So in this particular case, you can generate similar virtual population, but also some subjects of this virtual population right here will have synthetic aneurysm, small aneurysm or big aneurysm. And you can generate a lot of pulse waves and then analyze them in a similar fashion with the help of neural networks and other machine learning methods. So here are some examples of pulse waves with and without aneurysm. So we can see that in some examples, in some places, the pulse wave is very different for the virtual subjects without aneurysm, black one, and with aneurysm, with red one. In this particular study, it was shown that we can predict the detection of aortic abdominal aneurysm with the precision, with sensitivity about 87%, which is the very good precision for early detection and for this kind of a non-invasive screening. I would like to emphasize that this particular method relies on a simple photoplethysmography. It's very easy to obtain. You just put a sensor on your finger. You don't have to perform CT scans, MRI scans. Basically, this particular approach can be used for an early screening for this particular cardiovascular disease. And this idea, utilizing pulse wave analysis for screening, can be very promising because right now we have a lot of wearable sensors on the market, some smart watches, smart bracelets, some other detectors. So they've got some variable precision and accuracy, of course. And we also have some phone cases, like here, the one produced by the company Cardiac Quark. This is some case on the phone. You can put your thumbs on the phone, and this program will read your cardiogram and also photoplethysmography from your fingers. And it will read two pulse wave. Well, cardiogram, of course, is not a pulse wave, but at least it will read your photoplethysmography. And we performed a study in Sечеnovский University with the help of this Cardiac Quark device. So we had like 520 patients that performed this particular study. We got their readings for photoplethysmography and electrocardiogram. And then each patient was, of course, studied in university, in clinic. And we found some of them have diseases. And it turned out that through the analysis of this simple pulse wave, we can first of all calculate systolic and diastolic blood pressure with the precision about 5 millimeters mercury. And also we can diagnose diastolic dysfunction with the sensitivity about 0.84. And we can calculate low ejection fraction with sensitivity of 0.82. And I would like to emphasize that this low ejection fraction below 55% is a very early stage of this particular disease. This is a disease when your heart cannot pump out blood, when it pumps out very small amount of blood located in that was accumulated in your left ventricle. And if your ejection fraction is low, it means that something stops your heart from pumping blood efficiently. And if your ejection fraction is just about 55%, it's very hard to detect it yourself. But this kind of a technique can detect it with a rather high accuracy. So these methods are very good for screening. You don't even have to go to the hospital. You can just take the case, make some measurements, and the program will tell you that you've got some serious problems, probably. So maybe you've got some problems with diastolic dysfunction. Of course, you cannot use these results as the final diagnosis. You should go to the doctor and confirm it. But early detection of the disease is very important for its treatment. And such methods can help us a lot. And they also can, it's possible, thanks to this method, it's possible to treat a lot of people, because everyone has a phone and everyone can get such a case, or at least rent it. So in conclusion, I'd like to say that 1D and 0D blood flow models provide good approximation of pulse wave, and this enables us to create some synthetic databases that helps us to hone and develop new method for cardiovascular disease diagnostics. And also we can use some wearable sensors for early detection of cardiovascular pathologies and for population screening. Hopefully this will be implemented in foreseeable future. So thank you for your attention. If you've got any further questions, feel free to email me. I will be glad to answer.